So you've signed up for a class called Real Analysis. What's real analysis? What'd you sign up for? And this is really like an unfair cold question. So what's your impression about what this class is going to be? Yeah.
It's like kind of what you said earlier about proving the foundations of calculus.
Yeah, sure. Oh, wait, right here. So let's build that up a little bit. What is calculus? Like, what are the things that are calculus? Everyone did take like Calc 1 through 3 at this point, right? Okay. I don't know if Calc 3 is a prereq for this. Is anyone like taking Calc 3 right now? Okay. I think the natural flow is definitely not that. When I say calculus, what do you think of?
Derivatives.
Derivatives, cool. Yeah, so what's one thing you do in calculus? You study derivatives. And what's the philosophy of derivatives like? What is the derivative of a thing?
Instantaneous rate of change.
Instantaneous rate of change. Cool. And like, what does instantaneous mean? Like, instantaneous, yeah.
We can kind of just get like in on one exact point, like in between two numbers. Like there's always going to be more in there, and so we're looking at a precise number kind of.
Yeah, and I think like the buzzword you're looking for is limits. Yeah, so how do you do the instantaneous rate of change? You like compute a bunch of average rates of change, because those are easy to understand. And then you take a limit. So there's the big buzzword. We'll do a lot of things with limits. And in fact, maybe you remember this from like calculus. Like the derivative isn't the abstract thing. Derivatives are easy enough to understand as long as you understand limits. Limits are really where the meat is. So in fact, a lot of what we'll do will be studying limits in this class. And what do they actually do? And maybe the other thing you'll learn from calculus is like integrals. And what isn't the integral? When I say I'm integrating something, what am I doing? Yeah.
Finding the area under a curve.
Finding the area under a curve. And there's like a limity way to do that too, right? You say, well, I know how to estimate the area under the curve by drawing a ton of rectangles. What's the limit that I get when I use more rectangles? So it all boils down to limits and understanding. So that's a lot of what our game will be. And maybe there's not like a good answer to this question, what is real analysis? It's like asking, like, what is algebra? There's not like an actual compelling answer to that question. Maybe here's an attempt. So what are we going to do in this class when we study real analysis? We'll study the properties of the real line that have to do with, I don't know, proximity. And that's not like a great answer. But like limits have to do with proximity, right? They're like, what does it mean? What are these things getting close to? And even when you say like limits are infinite, you're saying, well, what does it mean to get close to infinity? And so it's all that philosophy. And maybe here's the first question. What are the real numbers even? And this is where real analysis will begin in this class. We'll say exactly what it is that we mean by the real numbers. And it'll take us a while to even do that. So this chapter that you have in front of you right now is background material on sets and functions. The next chapter that we will hit are the things that explain what are the real numbers even. It'll take us a while to go through that too. I guess I can drop these buzzwords right now. numbers are not area, are a complete ordered field. And I don't know, we won't focus on those words much today. We'll spend lots of time on them soon. Anyone recognize any of those three words as like things that have mathematical meaning? Which one?
Definitely field. We started talking about those at the end of abstract algebra.
Yeah, so if you've seen abstract, and I know that not everyone has, what's the idea of a field? Like, I don't want all the axioms because there are too many to list at once, but like, what's a field supposed to do?
It has a couple operations, so that, and they're closed. I haven't thought about abstract algebra since last semester.
So it's got some operations, plus and multiply.
Yeah.
And you can like undo both of them.
Yeah.
You can subtract and divide. And those things behave the way that you know that they ought to. That's the rest of the axioms. And we'll say what those mean in detail soon, because that's not formal. They do what you know they're supposed to do. What about ordered? What do you think that should mean in the context of the real numbers? I said the real numbers are ordered. What does that make you think of? Yeah.
One number is like greater than the one below it. I don't know.
Yeah, there's a sense of inequality. And the word complete is a little bit more abstract than the other two. Informally, it's like the real numbers have got no holes in them. There's nothing missing. Like if you only walk in the rationals, there's some things that are missing. If you only believe in the rationals, you'll notice that you're like, oh, I'm missing a square root of 2. The real numbers are what you get when you include things like that. And that's what the word complete is supposed to be there. But we're not going to do, well, maybe I should continue the overview. Once we get the real numbers, we'll start studying sequences of real numbers and their limits. There's a notion called cardinality, which discusses like sizes of sets. And this is a question that I think I'll be likely to get mostly noticed. How many people have taught the word cardinality in a mathematical context at some point? If I say the phrase, the real numbers are uncountably big, how many people have maybe taught something like that at some point? Yeah, that's a cardinality fact. We'll explain that in detail. But cardinality is the mathematical field that says there are more real numbers than there are natural numbers, even though they're both infinite. Once we hit that, we'll get to the idea of topology. We'll study things like open sets and compactness and what those abstract notions get you. Maybe I'll ask this. There's a course called point set topology. How many people have taken or are planning on taking that? Have taken or are planning on? Okay, so there'll be new notions. We'll talk about functions of real numbers after that, limits and continuity. And the last thing we'll do is limits of sequences of functions. And the motivation for that last set of words is, remember from Calc 2, like you studied power series at some point, right? Taylor series. And those are really strong in that the idea is that a power series is something you can like approximate with polynomials. But what do you really mean when you say I'm approximating a function? It means that these things should be close to each other. And exactly what you mean matters a lot in that context. And that's what we'll close the semester with. Neato. Before we can do any of that, let's just recall some set theory. Maybe before even flipping to the next page. What's a set?
Category of things.
Yeah.
A group thing.
Yeah. And I read like any definition like that is going to be like super non-rigorous because like then what's a category? And it turns out a category is like another resolved mathematical word or something different from a set, which is fine, right? I mean, it's like a collection of things, and then like you have to ask, well, what's a collection and what are things? The honest answer to that question is, the definition we'll give on the next page will be very loosey-goosey. It'll be basically what I just said. If you want to really know what a set is, then what you want to start studying is the axioms of set theory. And the starting point there is the words set and elements are undefined terms that satisfy some axiomatic conditions. And those axiomatic conditions are the Zarbello-Fraenkel axioms, and you usually have to add in this axiom of choice, which, if you want to study some like hardcore set theory, there are some good texts to go through. If you want a directed study at some point, it's a good topic. It's not really covered very well elsewhere. But yeah, what's the definition of a set? A set's a collection of things. These things are called elements. That's like a bad definition, right? So what we'll be doing is naive set theory. We're not going to go all the way to the foundations of mathematics just because we want to get to real analysis. So, what are sets? Let's just talk about ways to describe sets. One way to describe a set is just to list the things in the set. The set 1, 4, 7 is the set whose elements are 1 and 4 and 7. And that's just like a bit of language. Sometimes I'll use this set builder notation. I'll write down something like the set of all x such that x squared is equal to 4. And I didn't write those words, but that's what those string of symbols are supposed to mean. Yeah, maybe I'll say verbatim what I said before. So, I mean, I don't know, that's notation that people have seen at some point in the past, right?
What are you putting above 4?
Those are supposed to be quotes.
Okay.
Yeah. Yeah, both open quote and end quote, but yeah, I get that that's, yeah. That notation's familiar? Yeah, so let's just ask this question. Is 2 in that set? Why?
Satisfies the condition.
Yeah, satisfies the condition. 2 squared is 4. So 2 is in the set of all x values such that x squared equals 4. Nice. Let's maybe ask this question too. Could you describe that set in a different way?
All the x and the real numbers. Just 2. I'm assuming x is the real number, so 2 and 8 is 2.
Yeah, and this is real analysis, so in general, our things will be real numbers. Yeah. So, yeah. And you can be more flexible with this notation. You can write down something like this. Set of all things that look like 2 to the x, where x squared is equal to 4. Nice. All right. So, people feel pretty comfortable with those notations? Nice. And we'll use those notations. Obviously, those are just like toy examples that aren't terribly important. We'll come back to those. So let's now do some abstract set theory. So let's start with this. So suppose you have two sets. So they're collections of things. Then I will denote by A intersect B. The intersection of A and B is the set of all things that are both in A and in B. I don't know, maybe, I'm not 100% sure where everyone's background is. People have seen this symbol and associated it with the word intersection. Anyone know? Okay, cool. So the union is given by A union B, the set of all x's that are in A or in B, with the caveat that a mathematician's union is always inclusive. If you're both in A and in B, then the or is true. When a mathematician reads the words soup or salad, they're allowed to have both. That's allowed. Neato. Folks feel pretty good? Cool. The set difference. A set minus B is the set of all x's such that x is in A and x is not in B. Cool. All right, so let's just make sure that definitions feel comfortable. A is 1, 2, 3, B is 2, 3, 6. Determine those 4 things for me. And in general in this class, whenever I take a pause like this, just let people walk stuff like that out. The idea is that you can talk to each other. And some of you have undermined that by sitting very far away from anyone else. And that's fine if you want, but if you want to talk to other people, you can move now if you want. Cool. Folks feel pretty good? All right, let's just list them. What is, for these two sets A and B, what is A intersect B?
Just 3.
Just 3. Ooh, and I'm going to write something wrong. Why is that wrong?
It's going to be the set containing.
Yeah, 3 is not the set containing only 3. And often that won't be an issue because singleton sets aren't interesting. But you should make sure your categories are correct. What's their union?
Set containing 1, 2, 3, 5, 6.
All right, everything that's in A or in B, or in both. So 3 was in both, but it's still in the union. Set difference, A minus B. 1 and 5, sounds good. B but not in A. 2 and 6. All right. And right, nothing abstract has happened yet. I'm trying to warm into a few things. Set containment. If I say A is a subset of B, and I'll use this notation for subset. Sometimes in the literature you'll see that symbol for subset, which is fine. What does it mean? What does it mean to say A is a subset of B? Yeah.
All elements of A are in B.
All elements of A are in B. I think we're going to write this twice in 2 obviously the same meaning ways. All elements of A are in B. And I've used 2 different colors to emphasize that one of them is listing things, and the second one is what is true about those things. And maybe I'll write that in one other way, which will just sound more technical, but obviously mean the same thing. The more technical one, I think, will do more to tell us how to prove these sorts of statements, though. And so I'm about to write down something that's exactly the same as what you just said. For all A in A, it holds that A is in B. Oh. I'm sorry, was it doing that weird, coming in and out of focus this whole time? Oh, okay, that was the first time it happened. All right. The document camera sometimes decides it wants to focus on my hand instead of what I'm writing. And yeah. Cool, it won't matter. So that tells you something, 2 things important. If you want to prove a set is contained in another set, that means you want to prove something about everything in A. So probably if you want to prove A is a subset of B, you should probably start with the line, consider any A in A. It doesn't matter what letter you use, as long as it's consistent, which I haven't been in this sentence. And then you should conclude, eventually, that that element A is also in B. You could use X if you wanted to instead, but you should use the same letter on both sides. You know that. Folks feel pretty good? Cool. So, we'll do down here a demo of such a thing. So intervals. Let's put this in set builder notation. What is the interval from A to B if I use parentheses? So set builder notation is like the set of all x such that stuff.
It's all the stuff between A and B, but it doesn't include A and B themselves.
Cool. So the set of all x such that x is in between A and B, but x is in A and x is in B. That's correct, but it's like I haven't given myself enough space to write all that. It's like what's the short way of writing that? Yeah. Yeah.
Given S is greater than or less than B.
Yeah. That fits. I don't know. I was digging for A less than X less than B, which obviously means the exact same thing. What's the set builder for the closed interval?
Put a line under, make it equal to.
Yeah, less than or equal to. Set of all X. And right, these are X's in the real numbers. All of my sets are going to be subsets of the real numbers, except when they're not. But I'll be specific when they're not. They might be sets of sequences, right? Set of all X such that. Oh, and sometimes I'll use that colon symbol for such that, and like it's bad to be inconsistent, but I'll be inconsistent and I apologize for it. Nice. So that gives us set builder notations for these things. So we now know what it means to be in an interval. It means that some inequality is true. And we know how a proof of set containment should be formatted. So let's just see that in practice. Let's prove this. Let's prove that the open interval from 0 to 1 is contained in, is a subset of, the closed interval from 0 to 2. That look like something that's probably true? Let's try to come up with a proof. And the first and last lines are provided. And they're like the lines that you should come up with automatically. You want to show this is contained in that. First line has to be, consider any x in the interval from 0 to 1. And you know what the last line should be? It has to be a conclusory sentence saying it follows that x is in the closed interval from 0 to 2. So, how would you prove that? Let's go to the board and just try to come up with it. So you know, that's probably enough space. So I'm going to try to sketch a proof up here, and let's just follow our nose. What does this mean? What does it mean to be in that open interval? Yeah, but I'm going to write that in the more efficient way. And this is just like boardwalk, so I'm not going to write all the sentences. I will soon. I want to get x to be in there. So what does that mean that my eventual goal is? Yeah. So I need to come up with a way of saying, if I know that's true, then that's true. Tell me why.
1 is strictly less than 2.
And maybe I'll drop a 1 that y'all recognize. And so by transitivity of inequality, what do you get to conclude? Yeah. Oh, sorry, I thought I wasn't going to write all the words on the board, and I am. All right, so you know x is less than 1, 1 is less than 2, so x is less than 2. I want x to be less than or equal to 2, but that's obviously bigger. All right, cool. So I guess that buys me that much. That's good. I still need 0 to be less than or equal to x. Why is that?
0
maybe I'd sooner use some language like that. I know that 0 is less than x. It's easier to be less than or equal to something. So in particular, 0 is less than or equal to x. And maybe the closing blogs are if both inequalities are true, then we just write it as a single inequality. What do you think? Does that look like a proof? Ish. It's at least like the Scratch-Walk law proof. You wouldn't like show this to someone else. You would like write down the logs, but let's write down the logs now. So I started by considering any x in 0, 1. What was the next step in what's written up there? Yeah. So 0 is less than x is less than 1. All right. What was the next thing we did?
Less than 1, which is less than or equal to 2.
Maybe I'll even say strictly less than, because it's weird to say 1 is less than or equal to 2. I mean, it's true, but it feels weird to say. And then we use the word transitivity. Transitivity. Oh gosh, that spelling got way out of hand. I'm not going to fix it, though. Nice. So x is less than or equal to 2. What was the other thing we did? Yeah. Maybe I'll use like this sort of line. Since 0 is less than x, 0 is also less than or equal to x. All right. And why is that? Why does that make us happy? Why is this progress?
Those two statements combined are equivalent to the statement we were trying to prove.
So since 0 is less than or equal to x, and x is less than or equal to 2, we get 0 less than or equal to x, less than or equal to 2. And why does that make us happy?
That's the same as x is in the interval of 0 to 2.
Neat. So we can pick up with what's like actually typeset. There will be a lot of examples of times in this class where I haven't given myself enough space in these arguments, like enough lines written down. And so it's always like, I'm a little bit afraid I haven't given myself enough space. But this time I did a good job. I gave myself an extra line. We conclude that x is in 0, 2. And now let's just write down a conclusion, a real conclusion sense. Since we have that every x in 0, 1 lies in 0, 2, we conclude this subset, the set containment is true. Folks feel pretty good? Nice. And like, this was obviously like a fairly easy toy example. The main thing I want the takeaway to be here is if I ever ask you to prove one set is contained in another, either there's some fancy theorems you can use, or your proof is going to be consider anything in one, show what's in the other. All right, set equality. So, what does it, yeah.
That notation of 0 is less than equal to 0 and 1 is less than equal to 2.
Yeah. I'm not a huge fan of it.
Seems like you're treating them like a set union, like, oh, one's part of the set that is less than equal to 2.
Oh, sure. Yeah, so in some sense, so inequality does behave similarly to like set containment. There's a reason that the symbols look similar. And there's like a non-rigorous thing we're doing right now. So the axioms of the real numbers are like, one of them is it's an ordered field. So we need to explain what that really means. One of the rules we'll develop in a few days when we talk about ordered fields in more detail is if 0 is less than x, then 0 is less than or equal to x. So we will make that rigorous soon. along with things like transitivity. 1 is less than 2, and x is less than 1, and 1 is less than 2 means x is less than 2. That's something we need to prove, or justify in terms of our axioms somehow. Yeah, so there are things that should make you slightly uncomfortable in terms of rigorousness right now, but it's unavoidable because you can't build something from nothing, and I don't want to start all the way back in set theory. Nice. That's a reasonable objection, though. Nice. So, I've got a few minutes left. Set equality is the last thing to think about. What should it mean to say two sets are equal? I know stuff's written down there, but yeah.
If you do set subtraction on them, they end up as the same set as they were before.
Oh, sure. I'm not going to make that the definition, but I think that's a good feeling. Where that means the empty set symbol, which is a symbol I haven't hit yet, but we will in a moment. I think that's a property, and it's like sufficient to be a definition, but I don't think I want that to be the definition. Yeah.
If the two sets are subsets of each other.
Yeah, and I guess like that's what's written down too, right? Is it what's written down? Yeah. Right, and like that makes some sense, right? Two sets should be equal if they contain the same elements. So everything that's in one should be in the other because they're the same damn set. Everything in the other should be in one. So we say A is equal to B if these two set containments are true. And what does that mean? So that means if I ask you to prove that two sets are equal, there are two things I'm asking you to prove. I'm asking you to prove A is a subset of B and B is a subset of A. So if I ask you to prove a set equality statement, really I'm asking you to prove two set containment statements. And I think we have enough time to like start a demo if you want. Let's prove this set equality. The set containing only -1 and 1 is equal to the set of all x's whose square is 1. Oh yeah, there's an example of this inconsistency. I'm trying to use a vertical slash and not a colon for the such that. If you use a colon instead of a vertical var for the such that, I'll be just fine. I won't object to that. So, just because it's on the previous page. You want to prove that set equality statement, so you need to prove two set containment statements. So there'll be two steps in this proof. First, prove that set containment, then prove the reverse set containment. And how long time is that? No, that's fast. I've got like a minute 30. Let's try to prove one of them. Let's make some progress improvement. Let's analyze what the proof should look like anyway. So let's suppose you want to prove this first set containment. Prove that the set containing -1 and 1 is contained in the set of all x's whose square is 1. So if you want to prove that, like, what should your starting point be? What do you get to assume?
Either A is -1 or A is 1.
Yeah, and that's even like the second line, right? Really the first line should be consider something in the set containing -1 and 1. Sorry, there's awkwardness in that like things are written already and I'm also trying to be organic. Yeah, so you get to consider anything in 1 or -1. Well, there are only two things, so let's just do it one case at a time. It's either 1 or -1. I don't have enough time to finish, so let's jump right down to what like the goal will be. If I want to prove this set is contained in the other set, what should be my goal? What do I need to prove about A? A squared is 1. And again, that's like one step to remove. Really, that's what I want to prove. That's my goal. But that goal means the exact same as what you just did. So that's actually an important step in trying to come up with a proof. Unravel the definitions of the things you assume. You get to assume A is in -1, 1. Well, there are two things it could be. Your goal is showing A is in the set of all x's whose square is 1. That means you need to show A squared is 1. And I think that means that it's time for my office hour. Anyone planning on coming to my office hour now? All right, that's fair enough. And you don't have to tell me in advance. I don't need warning for office hours. Cool. So we'll pick up roughly here next time. In terms of pacing, maybe I'll see how people feel. I'm trying to start up with a fairly gentle push-in. Oh, maybe I'll point out homework. So the homework associated with these, like it is listed in Canvas, and Canvas will link you to this, where the homework begins. And I think you know enough to, yeah, start looking at really all of them. Yeah. We'll do more proofs in this kin, but take a look at those. It'll give you some motivation for what we're going to do next time.
Do you have a LaTeX template that you use at all?
I can give you one. Yeah.
That would be nice.
Yeah, so in terms of homework, I'm not going to demand that you tech anything for the homework. If you would prefer to tech things and want a starting point, I'll give you one. If you have your own templates you like to use, I'm not picky about exactly how things are formatted.
I think the template would be helpful if you already have it.
Oh, I'm sure I do. Yeah. Thank you. See you in 2 days.